Well, hello and welcome to Doc Onco's Physics once again. My name is Keith Onco, and what we're going to be doing today is taking a look at the EMF developed in a loop of wire and also the direction of the current in that wire given the change in the magnetic field that it encounters. So over on the left-hand side, I've placed the equation for the EMF, and EMF just stands for electromotive force, which is sort of an old style word for voltage or phrase for voltage. And the electromotive force is equal to the, get the pen going there we go, is equal to the negative of the number of loops of wire in whatever it is we're working with, times the change in the magnetic flux in the inside of that coiled wire, divided by the time it takes for that change to occur. So let's say, and I'll create a little loop over here on the right hand side. Say I've got a loop, a loop of wire there. And it's going to travel into a magnetic field that is going into my page. Okay. And we'll say that the magnetic field has a strength B is equal to 0.0. I'll change it up this time. Make it 0.6 Tesla. Okay. Now, initially, my loop of wire is not in a magnetic field at all. Okay. And so the magnetic field initially is going to be 0. So B initial is equal to 0. Okay. The area of my loop, let's say that it is, we'll make it 10 centimeters on this side and 20 centimeters on this side, so 0.2 meters and 0.1 meters. And so our area is going to be 0.1 meters times 0.2 meters, which turns out to be 0.02 meters squared. So there's the area of the loop that we're going to be working with. The area is not going to change. All right, but the magnetic field is going to change. So now let's say that I take this magnetic field right here, this loop of wire right here, and I move it quickly into the magnetic field, and the time that I take to move it into the magnetic field is 1/10 of a second, or 0.1 seconds. After it moves into the magnetic field, I move the entire loop in the magnetic field, and so the magnetic field B final becomes 0.06 Tesla. Okay, so my equation, if I look at it up here, is the voltage or the EMF that gets developed in the loop is going to be minus the number of loops of coil. Well, in this case, I only have one, so N equals 1, all right? N is equal to 1, times the change in the magnetic flux, delta phi, divided by the time, the change in time. Well, the change in time is 0.1 seconds. So we already have that. The change in the magnetic flux is going to be the final magnetic flux minus the initial magnetic flux. Well, the final magnetic flux is going to be 0.06 Tesla times the area, 0.02 meters squared, minus the initial. Well, the initial is BI, which is 0, right? So we had 0 Tesla. It's a funny looking T there, times 0.02 meters squared, okay? So this part of the equation just sort of drops out, right? And so we get 0.06 times 0.02, and this, when we multiply it out, becomes 0.0012. So the change in the magnetic flux is 0.0012 Webers. Okay? That's delta phi. Okay, so if I want to find the voltage, right, that gets induced in this one wire loop, what I have is I have the number of the negative of the number of wire loops. Okay, so let's see if we can do that. There we go. So it's going to be the -1 times 0.0012 Webers divided by 0.1 seconds. And what that turns out to be is simply -0.012 volts. Not a very large voltage, right? Pretty small. Okay. How could I increase that voltage? Well, let's say I had 100 turns in this wire loop instead of 1 turn, right? What we do is we would multiply the 0.012 volts by 100 and we would get 1.2 volts. Now I have a decent amount of voltage. Now, one of the other interesting questions we might have is this. As I move this loop into the magnetic field, and so then the loop becomes completely in the magnetic field in here. All right, so I've moved it in the magnetic field. What is the direction of the current in the actual loop itself? Okay, a good question. Well, in order to do that, I've got to ask myself, what is it about the loop that is going to create, or why is it a current that's going to get created in the loop itself? Well, as I mentioned in the video lesson, the wire loop or solenoid likes to keep the status quo. It does not like change. Okay. Well, in this case, because I move my wire loop into the magnetic field, right? So now it's in this magnetic field over here, right? It's in that magnetic field. What's changed? Well, I went from no magnetic field inside of the wire loop to a magnetic field pointing into the board, or into my board. What's the loop going to try to do? It's going to attempt to create a magnetic field to oppose the change that it has undertaken, right? So it's going to create a magnetic field pointing out of the board, right? So it will create, and I'm going to put this in red, if I can find red there we go. So it's going to create a magnetic field pointing out of the board, all right? So what would the direction of the current be in the loop itself? Well, this is where I'm going to have to use the right-hand rule again. And the right-hand rule that I'm going to use is the one where my thumb points in the direction of the magnetic field and my fingers curl in the direction of the current. So from my perspective, it's going to be my thumb is pointing out of the page or out of the board and it's pointing at me, and my fingers are going to curl in a counterclockwise direction so that the current is going to flow in a counterclockwise direction around the loop. Okay, so that's how to determine the EMF that gets developed in the loop, and that's also how to determine the current that gets generated, the direction of the current generated in the loop. Let's take another look at a slightly different problem. Let's say that I have a current carrying wire up here. There's a current carrying wire, and below it I've got some circular loop. And let's say that in this particular case the current is increasing. All right, I would like to know what's going to be happening inside of my loop of wire here. What's the direction of the current going to be inside the loop of wire? Well, let's take a look at this. We have a current carrying wire up here, right? And let's make this just a tad bigger here. I've got a current carrying wire, right? And the current is increasing. Well, let's forget about the fact that the current's increasing for a minute. What would the direction of the magnetic field be below the wire where the loop is, down here? Well, again, I'm going to have to use the right-hand rule. And in this case, my thumb is going to point in the direction of the current. So my thumb's going to point to the right, okay? And the current, or I'm sorry, the magnetic field on the top of the wire will be coming out of the page. And on the bottom of the wire will be going into the page. So everywhere below the wire, I'm going to have a magnetic field going into the page. everywhere below here. Okay, and again, I had to use the right-hand rule to do that. And the right-hand rule again was thumb points in the direction of the current, and my fingers curl in the direction of the magnetic field. Because remember, there's a magnetic field surrounding this current carrying wire, right? Concentric circles around the current carrying wire, all the way through this loop here. Well, now, this case here says that the current is actually increasing. So what's happening is the magnetic field inside of my loop is increasing. So what is the loop going to try to do? It is going to try to create a magnetic field in the opposite direction, right? And since the magnetic field is increasing due to the external magnetic field created by the wire, it's going to try and create a magnetic field that opposes that magnetic field, right? Because remember, the current up here is increasing, right? This current's increasing, which means this magnetic field here is increasing below. And so the loop does not like the change, and so it's going to try to create a magnetic field that opposes that, and so it will create a magnetic field coming out of the page or out of the board. Well, again, I'm going to have to use a right-hand rule if I want to know the direction of the current in the loop, and it's going to be the right-hand rule where my thumb now points in the direction of the magnetic field, which is out of the page, and my fingertips will curl in the direction of the current in the wire loop, which is going to be, again, it's going to be counterclockwise. So the current in our wire loop is going to go counterclockwise. All right, I hope that helps, and we'll see you next time.